The audience that this video is intended for is a Calc 1 or Calc 2 student who's getting just kind of a quick preview of differential equations. This is not a full-blown differential equations type video. In Calculus 1 and 2, we give a little taste of what differential equations will cover, and that's what we're going to talk about in this video. So just a quick summary, a quick short definition of what a differential equation is it's going to be an equation that contains at least one derivative, thus the name differential equation. So you might have what's known as a first order differential equation, like the first one here, in which case you only have a dy dx, a first derivative, or look at the third equation here. This is a second order differential equation because you've got up to y double prime. Now, in Calc 1 and 2, when you study differential equations, they will remain quite easy, quite on the simple side. When you take the full-blown differential equations course, that's when you'll get into more involved differential equations that require some advanced techniques. Okay, so here we go. Just take a look. Here are three examples of differential equations. First one, dy dx equals 2x minus 7. It's an equation that has a derivative in it. So it's a differential equation. Sometimes instead of dy dx, we'll write it with a y prime. Look at the second equation. 3x y prime minus 6 equals 0. And the third equation is a second order differential equation. Y double prime minus 2ty prime plus y equals e to the t. So this has the original function, the first and the second derivative in it. All three of these are examples of differential equations. Now, the big question we have now is, what do you do with them? Like, what's the answer to one of these guys? You know, what exactly do we solve for? Well, here's a couple comments. A solution, here's what an answer is. Here's what a solution is. A solution to a differential equation is some function that makes the equation true when you plug it into the dependent variable. So, for example, in the first equation we have, like right here, for example, is some function that if you took its derivative with respect to x, its derivative would be 2x minus 7. For the second equation, it would be some function if you took its derivative times 3x and subtracted 6 from that, you would get 0. Now, admittedly, these sound really hard just to kind of dream up the answer off the top of your head. Fortunately for us, there's a systematic way to chew through these problems and get our answer. We don't just have to dream up the answer. The last one obviously sounds like the most complicated of all. The solution to this one would be some mystery function, so that if you took its second derivative minus 2t times its first derivative and added to that the original function, they would all wind up canceling and simplifying and reducing to just e to the t. Very, very hard just to mentally just guess a function like that. All right, now here's our goal though. We want to find that solution. So how do we do that? Well, it all keys on this second observation right here. There are some first order differential equations. First order, if you remember, means that it has first derivatives only, that can be solved using this new thing that we've been talking about, integration. Now, why is this? Well, if your equation has a derivative, how could you bring back the original? What's the opposite of differentiation? Well, it's integration. And here's the idea. If you had a differential equation that was dy dx, first order, and you had the dy dx on the right-hand side, on the left-hand side, and the right-hand side only had x's, then you could reorder these terms as dy equals f of x dx. Now, there's a name for that. Now, normally we just give this name in the differential equations class, but I'll go ahead and mention it now just for the heck of it. This is called separation of variables. Separation of variables. And the way that it works, or the reason that it works, is because if you can separate the variables y's from x's or y's from t's, etc., then you can integrate the left-hand side and integrate the right-hand side, and the dy and the dx are your variables of integration, and it brings back the original. So the integral of 1 with respect to y would be y, and the integral of f of x dx, assuming we can take that integral, that would yield our answer, All right, so let me show you one, because maybe this will click a little bit better as we do an example. So here's a quick one. dy dx plus 1 equals 2x minus 6. So if we wanted to categorize this guy, we would call him a first order differential equation, right? And so what do we want to do? Well, first step, we want to solve for dy dx. So we'll take dy dx equals 2x and then subtract 1, so we'd have minus 7. Then we move the dx to the right, so we have dy equals 2x minus 7 dx. I've separated the variables here, so I'm going to integrate both sides. The integral, as I said earlier, of the number 1 with respect to y would be y, just like if we integrated the number 1 with respect to x, we'd get x. So the left-hand side would be y with no integral symbol, and the right-hand side, the integral of 2x minus 7, would be x squared minus 7x. All right, and then you might remember a couple of videos ago when we studied indefinite integrals, we were always supposed to put a plus c. So I am going to put a plus c, but you might have a question. You might say, well, Devin, why did you not put a plus c on the left-hand side? Well, in actuality, we could have, but it's really not necessary, because if you wrote like a plus c1 and then a plus c2, let's say over here, these constants clearly don't have to be the same. And so if you subtracted the c1 over to the right and absorbed it with the c2, one constant plus or minus another constant would, at the end of the day, just wind up yielding just a new constant. So you only have to put it on one side or the other. So this guy right here, this would be the solution to this differential equation. And so anybody of this form, x squared minus 7x plus any constants derivative, if you added 1 to that, would give you 2x minus 6, meaning it makes the differential equation true when we sub this in everywhere that there's a dependent variable like y. Now there's no y's in here, but there is a dy dx. So when you sub this guy's derivative in here, it makes the equation true. Let's close off this video with one last example. dy dt equals 6t squared. Again, this is a first order differential equation. It's what we call separable, meaning that we can separate the variables. So let's do that. So we're going to put the y's on the left, and we'll move the t's to the right. 6t squared dt. All right, we'll integrate. Integral of the left-hand side, there's an understood 1 here, that'd be y. Integral of 6t squared would be 2t cubed plus c. So that would be the solution to this differential equation. Now I should probably clarify, is every first order differential equation separable? No, you can't do this to every first order differential equation, but simply my point is that if it's separable, if you can separate the variables, then we can solve it using integration. So if they're asking you to solve a differential equation in a Calc 1 class or a Calc 2 class, chances are, in all likelihood, it will probably be separable. There are a couple of other techniques that we have that'll still solve them even if it's not separable, but the vast majority will probably be separable like these, where you can separate the dependent variable from the independent variable.